Hi, welcome to Bayes' theorem in pictures. In this video, we'll be talking about Bayes' theorem. Bayes' theorem is an important relation in probability and is critical for interpreting data. We'll briefly review the notation in Bayes' theorem and then do an example. First, we'll work through the example without using Bayes' theorem explicitly, and then we'll go back and see how what we did relates to the theorem. At each stage, the equations will be accompanied by pictures to show how the various quantities are related to each other. Here, our emphasis will be on doing an example. We will basically be looking at the same concepts as we did in the video Introduction to Bayes' Theorem. If you watched that video and everything was crystal clear, you might not need this video. Okay, let's get started. So Bayes' theorem looks like this. It says P of A given B equals P of B given A times P of A divided by P of B. So let's define that notation. So P of A is the probability of A, and P of B is the probability of B. P of A given B is the probability of A given that B is true, and P of B given A is the probability of B given that A is true. So note that P of A is the probability of A being true without using any information about whether or not B is true. And also, P of B is the probability of B being true without using any information about whether or not A is true. On the other hand, P of A given B and P of B given A are conditional probabilities. So if B is true, then P of A given B is the probability that A is also true. So let's see how we would read Bayes' theorem. So it reads as follows. The probability of A, given that B is true, is equal to the probability of B, given that A is true, times the probability of A divided by the probability of B. Okay, now let's get to our example. Let's say you have a farm, and on this farm you have 100 animals. 70 of the animals are cows, and 30 are horses. Of the 70 cows, 45 of them are black, and 25 are brown. And of the 30 horses, 5 are black, and 25 are brown. Now, you go away on a trip and hire an inexperienced farmhand to watch the animals while you are gone. You call up the farmhand and ask how things are going. The farmhand tells you that one of the animals ate much more food than each of the others. You ask whether it was a cow or a horse, and the farmhand replies, "I don't know, but it was black." So you make a mental note to fire your farmhand when you get back. But in the meantime, let's figure out the probability that the animal in question was a cow or a horse. So there are 100 animals, so let's represent each animal as a square on a 10 by 10 grid. 70 of the animals are cows, and 30 of the animals are horses. We'll let the top 70 squares represent the cows, and the bottom 30 squares represent the horses. If an animal is chosen at random, there's a 70% chance that it's a cow, and a 30% chance that it's a horse. But the farmhand said that the animal was black. Let's see what that tells us. Of the 70 cows, 45 of them are black and 25 are brown. Of the 30 horses, 5 are black and 25 are brown. let's color code the square representing each animal. Now, your farmhand didn't know if the animal was a cow or a horse, but said it was black. So let's look at the black animals and see how many are cows and how many are horses. So there are 45 black cows and 5 black horses. This gives a total of 50 black animals. So 90%, that's 45 out of 50, of the black animals are cows, and 10%, that's 5 out of 50, are horses. So, given that the animal is black, the probability that the animal is a cow is 90%, and the probability it is a horse is 10%. So, we know how to get the answer to our question using the picture. But believe it or not, we've just used Bayes' theorem. Let's write down Bayes' theorem and find out how it relates to the picture we just drew. So, Bayes' theorem is P of A given B equals P of B given A times P of A divided by P of B. So let's get the probability that the animal is a cow given that the animal is black. So we'll set A equal to animal is cow and B equal to animal is black. We'll abbreviate these as cow and black respectively. So the probability that the animal is a cow given that the animal is black is written as P of cow given black. Let's fill in the rest of the A's and B's in Bayes' theorem. Okay, so that gives us that P of cow given black equals P of black given cow times P of cow divided by P of black. Okay, so we have our equation resulting from Bayes' theorem. However, it may be easier to see what's going on if we move the term in the denominator to the left side. So that gives us P of cow given black times P black equals P of black given cow times P cow. We'll use this form. Okay, so again we have that same equation. Let's see how each factor in this equation relates to our 10 by 10 grid. We'll start with the factors on the left-hand side, P of cow given black and P of black. Note that P of cow given black is what we just calculated, but we'll go through it again. So, to get the probability that the animal was a cow, given that it was black, we took P of cow given black equals the number of cow black squares, shown here in the pink outline, divided by the total number of black squares, now shown in the pink outline. That gives us 45 over 50, and that was 90%. Okay, so that's the result that we already knew. Now let's do the other term on the left-hand side of our equation, P black. So P of black is the probability of the animal being black without regard to its being a cow or a horse. So P of black equals the number of black squares, shown in the pink outline, divided by the total number of squares, which is all 100 squares. So that's 45 plus 5, which is 50, divided by 100, which equals 50%. So P of black equals 50%. Okay, so at this point, our equation looks like this. On the left-hand side, we have P of cow given black, which equals the number of cow black squares divided by the number of black squares. And we have P of black, which equals the number of black squares divided by the total number of squares. Now, we can already see that on the left-hand side, the factors of number of black squares are going to cancel. Okay, now let's look at the factors on the right-hand side, p of black given cow and p cow. Okay, so p of black given cow is the probability of the animal being black, assuming that it is a cow. So p of black given cow is equal to the number of black cow squares, shown here in the pink outline, divided by the number of cow squares, now shown in the pink outline. So that was equal to 45 over 70, which is about 64%. And now, p of cow is the probability of the animal being a cow without regard to its color. So this is given by p of cow is equal to the total number of cow squares, so that's the 70 in the top part of the grid, divided by the total number of squares, which is 100. So that gives us 70 divided by 100, or 70%. Now our Bayes theorem equation looks like this. On the left-hand side, we have the same thing as we had before. But now on the right-hand side, p of black given cow is equal to the number of black cow squares divided by the number of cow squares, and p of cow is equal to the number of cow squares over the total number of squares. So this time we can see that the factors of number of cow squares will cancel on the right side of the equation. So in pictures, our equation looks as follows. So on the left-hand side, we have p of cow given black, p black. Now p of cow given black equals the number of black cows divided by the number of black animals. And p black equals the number of black animals divided by the total number of animals. On the right-hand side, we have p of black given cow times p of cow. Now p of black given cow equals the number of black cows divided by the number of cows, and p of cow equals the number of cows divided by the total number of animals. Now, note that both sides of this equation give the probability of the animal being a black cow. You could multiply both sides of the equation by the total number of animals, n, to get the number of black cows on each side. So p of cow given black, p of black times n is equal to p of black given cow, p of cow, n. So let's look at each side of this equation. On the left-hand side, we have p of black times n. That's just the number of black animals. When we multiply that by p of cow given black, we get the number of black animals that are also cows. On the right-hand side, we have p of cow times n. That gives the number of cows. And then we multiply that by p of black given cow. And that just gives us the number of cows that are black. Either way, you end up with the number of black cows. In our example, Bayes' theorem is just a statement that the number of black animals that are also cows is the same as the number of cows which are also black. Now, we can similarly make a more general statement about Bayes' theorem by moving the denominator in the usual equation to the left-hand side. So we take p of b in the denominator of the right side and move it over to the left side. So let's look at that equation. P of a given b times pb is equal to the probability of a and b. And P of B given A times PA is the same thing, but with A and B exchanged. So Bayes' theorem is a statement that the probability that both A and B are true is the same as the probability that both B and A are true. Okay, so let's summarize. Here we've seen a use of Bayes' theorem utilizing pictures and hypothetical farm animals. If you'd like to learn more, you might be interested in the other videos in the Bayesian playlist, available on this channel.